Let's consider a few more examples using implicit differentiation. Find dy dx of x squared y plus xy squared equals 2x at the point 1, 1. So I'm going to have to use the product rule a number of times here. So by the product rule for x squared y, the derivative would be 2x times y plus x squared times 1 dy dx plus, now I'll have to use the product rule again on xy squared, whose derivative will be 1 times y squared plus x times 2y dy dx, and that needs to be equal to 2. I'm going to isolate all my dy dx's, so that will give me x squared dy dx plus 2xy dy dx equals 2 minus 2xy minus y squared. When I factor dy dx out, I'm left with dy dx times x squared plus 2xy equals 2 minus 2xy minus y squared. So dy dx is equal to 2 minus 2xy minus y squared, 2x, y minus y squared all over x squared plus 2xy. And since I'm looking at the point 1, 1, this will work down to 2 minus 1 over 1 plus 2, which is negative 1/3. A lot of product rule on that problem. Another example. Let's find dy dx of x plus y squared plus y equals 2 at 0, 1. By the chain rule, the derivative of x plus y squared is 2 times x plus y to the first times the derivative of the inside, which is 1 plus 1 times dy dx. This is plus the derivative of y, which is dy dx. This is going to be interesting. And this will equal 0. So it looks like, I can't see a better way to do this, in order for me to get dy dx by itself, I'm going to have to multiply this stuff out. So this will end up being 2x plus 2y times 1 plus dy dx plus dy dx equals 0. And when I expand this, I get 2x plus 2x dy dx plus 2y plus 2y dy dx plus the dy dx that was already there equals 0. I'm going to both gather my dy dx's and factor at the same time. So on the left-hand side, I'll have dy dx times 2x plus 2y plus 1. And when I move everything that didn't have dy dx over, I'll have on the right-hand side negative 2x minus 2y. Dividing to isolate, dy dx equals negative 2x minus 2y over 2x plus 2y plus 1. And since we're looking at the point 0, 1, this will simplify down to negative 2 over 3. In this problem, we're being asked to find the second derivative. So, using implicit differentiation, we'll get started. This will be 2x plus 2y dy dx equals 0. And this means that when I subtract 2x and divide by 2y, then dy dx equals negative x over y. Now if I take the derivative of both sides again, I'll show the notation, the derivative of this side must equal the derivative of this side. So on the right hand side is where I get my notation, the second derivative of y with respect to x twice. The derivative of negative x over y has to be done using the quotient rule. So this will be negative 1 times y minus negative x times dy dx all over y squared. But I already know what dy dx is from up here. It is negative xy. So by substitution, this will become negative y plus x times negative x over y all over y squared. And I'll clean this up a little bit. So this is negative y minus x squared over y all over y squared. And clean this up a little bit more, I'm going to divide both pieces by y squared, so this will be negative 1 over y minus x squared over y cubed. The final example is find the points where the curve has a horizontal and vertical tangent line. What an ugly looking curve. So the curve we're being asked for is, so we're being asked for this curve, and we'd like to know where it has horizontal and vertical tangent lines. Well, I know a horizontal tangent line has a slope of 0, and a vertical tangent line would have an undefined slope. So I want to know where the slope, or where dy dx is both 0 and undefined. So first I've got to get dy dx. The derivative by implicit differentiation would be 50 x squared plus 32y dy dx plus 200 minus 160 dy dx plus 0, and that will equal 0. I'm going to solve this for dy dx by isolating things. So I will have on the left dy dx times 32y minus 160 equals negative 50 x squared minus 200, and dy dx equals negative 50 x squared minus 200 all over 32y minus 160. So I have an expression for the slope at every point. This will equal 0 when the numerator equals 0, so that's where I will have horizontal tangents. And solving this for x squared, I will add 200 and divide by negative 50. And that will give me negative 4. And x squared cannot equal negative 4, so it will never equal 0. This will be undefined whenever 32y minus 160 equals 0. So 32y, let's just erase it. 32y equals 160 when y equals 5. And y will equal 5 with this given x value, and the directions are for me to find the points. So I'm going to need to go back to the original equation and substitute in 5. So we'll have 25 x squared plus 16 times 5 squared plus 200x, uh-oh, I'm running out of room, minus 160 times 5 plus 400 equals 0. Let me clean up this quadratic and get a little neater. So this will be 25x squared plus 200x equals 0. I can solve this by factoring out a 25x and having left x plus 8. So we'll have a vertical tangent when x equals 0 and when x equals negative 8. And this means the points are 0, 5, and negative 8, 5. A lot of implicit differentiation and a lot of algebra.